In this video, we present a complete short proof of the celebrated Fermat's last theorem. In number theory, Fermat's last theorem states that the equation, a to the n, plus b to the n, equals c to the n, has no solution in positive integers a, b and c, as long as n is an integer greater than 2. The proposition was first stated as a theorem by Pierre de Fermat around 1637, in the margin of a copy of a book called Arithmetica. Fermat added that he had a proof that was too large to fit in the margin. Although other statements claimed by Fermat without proof were subsequently proven by others and credited as theorems of Fermat, for example, Fermat's theorem on sums of two squares. Fermat's last theorem resisted proof, leading to doubt that Fermat ever had a correct proof. Consequently, the proposition became known as a conjecture rather than a theorem. The claim eventually became one of the most notable unsolved problems of mathematics. Attempts to prove it prompted substantial development in number theory. After 358 years of effort by mathematicians, the first successful proof was released in 1994 by Andrew Wiles, and formally published in 1995. It was described as a stunning advance in the citation for Wiles' Abel Prize Award in 2016. The Pythagorean equation, a square plus b square equals c square, has an infinite number of positive integer solutions for a, b, and c. These solutions are known as Pythagorean triples. The simplest example is given by 3, 4, and 5. Although the theorem has long been associated with the Greek mathematician-philosopher Pythagoras, it is actually far older. 4 Babylonian tablets from circa 1900 to 1600 BCE indicate some knowledge of the theorem, with a very accurate calculation of the square root of 2, and lists some Pythagorean triples. For example, from this 3,700-year-old Babylonian tablet, Plimpton 322, at the Rare Book and Manuscript Library at Columbia University of New York, it is mentioned that 4,601, 4,800, and 6,649 form a Pythagorean triple. Back to Fermat's theorem. We need to prove that the following set is empty. Or equivalently. It is easy to see that if the triple, A, B, C is in FPQ, then the triple AQ, BQ, CQ is in FP. Consequently, it suffices to prove that the set Fn is empty for prime numbers n greater than 2. We can also write C equals A plus H for some natural number H, therefore, we are done if we show that. We assume to the contrary that Fnh is not empty, that is, there exists a pair of natural numbers, AB satisfying. Applying the mean value theorem to the function, f of x equals x to the power n, on the interval, a plus h, there exists a real number t between a and b, such that, since the right-hand side is equal to b to the n, it must be of the form, h to the n, times n to the n, times q to the n, for some natural number q. Next, we expend the left-hand side. If GCD of n times h, and a equals L, the factor L to the n can be cancelled in the equation. Therefore, we may assume without loss of generality that GCD of n times h, Na equals 1. This yields a contradiction, because the right-hand side of this equation is divisible by nh, at most once, while its left-hand side is divisible by nh, at least n times. This completes our proof.